It could be, yeah. Kind of a small class, but we'll definitely get through it.
I know Coach Pelican has a pretty big, flu going around South Lake.
Yeah, dang. Flu is the worst. It feels like you're literally dying. So I feel for those people. Thank you.
Yeah, and made a minor correction since I forgot to reprint it.
Oh, good
Since
call on
that-
that.
Yep, since I just crossed out and put a height.
That works great. Thanks. Thank you. Welcome back, everyone. We're about to finish off week 6 out of the 16-week semester. Our goal today is just to move through chapter 14. We looked into confidence intervals, and now we're turning it over to a new kind of analysis, the hypothesis testing. A lot of people are possibly familiar with this, but our class is weird. We don't have any statistics as a prerequisite. So we're going to cover hypothesis testing from the top bottom, and then that will finish off chapter 14. And really that's in the spirit of what chapter 14 is all about. It's a heavy, heavy introduction to statistical inference before we get into the more sound methods in chapter 17. And maybe just one more warning. For a lot of this material, it might feel like it's a rehash or not too difficult. Chapter 13 was a rough spot, but chapter 13 is rough just because it's abstract. Chapter 15 coming up next is a little bit rough because has a lot of moving parts. It's technical. We're going to talk about type 1 errors, type 2 errors, expressing exactly what they would mean in a particular situation, and trying to manage which one is best to avoid, which will inform us how we decide to write out our hypothesis test by saying the significance level we're going to target. So lots to discuss in chapter 15. But once we get through that, we'll just be doing statistical method after statistical method, just collecting as much as we can through to the end of the semester. So that's where we're at. That's where we're going as well. Any questions at all, folks, to start us out today before we jump back to 14? Okay, let's get started then. So we left off right here. It's a wall of text. I know it's kind of rough at sometimes, but there's a lot to say about hypothesis testing. So this is about as terse as it can get, really. Let's run through the definition. When we say hypothesis testing, it means we really have two claims. One of them is going to be assumed true by default, and the other one is the actual one we're looking for evidence to support. It says here, the claim being tested is called the null hypothesis. We assume that to be true right at the very beginning in hypothesis testing. We denote it by H naught, and the claim we're trying to find evidence for, we can either call it the alternate hypothesis or the alternative hypothesis. Either way, we're saying the same thing. And we denote it by HA. That's lowercase a or uppercase a, same difference. So the analogy is a court of law, which is a really strong analogy because the logic in an actual courtroom setting, say maybe you got pulled over for a speeding ticket and you got summoned, they're going to use this exact logic on you. We've probably all heard all the time, in a court of law, the null hypothesis is that the defendant is assumed to be not guilty. And we make that assumption right out of the gate. H naught is true. But we reason with that being the truth of what's going on with the defendant. The prosecuting attorney plays the role of the statistical researcher. Us, being the statistical people, are trying to show that this is true. And what we'll use is probabilities in place of evidence. So we're trying to find evidence against H naught. In other words, we're trying to show that the assumption of H naught being true is so unreasonable against the statistical evidence that we've gathered that we are forced to saying H naught is actually false, and we'll accept the alternate reality. The alternative hypothesis HA was actually true. So we use probabilities to make that determination. And as the notes kind of indicate, lots to discuss on this kind of stuff. But this is the major idea with hypothesis testing as it starts. This is an analogy that just about every textbook likes to discuss because I guess we watch a lot of court TV, maybe in America. but also because it really is the same kind of logic. Any questions at the moment, folks, with just the first core definition here? Okay, well, when we go to write out our actual null hypothesis and our actual alternative hypothesis in a statistical setting, it's going to take on one of these different roles for the alternative, and our textbook is a little bit odd. Our textbook only ever puts equality right there for the null hypothesis. For people who have studied statistics in a different setting, in particular out of the biometry lab, you know that there's actual options here. It could be less than or equals, greater than or equals, or a dead-on equals. Our author has reasons for only using equality there, but it is definitely weird when you're setting up these hypotheses for the first time. So we'll mention that as we work through the notes, that there are more than one ways to state your null hypothesis correctly. Major thing, though, is in your alternative hypothesis, there cannot be any hint of equality whatsoever. Either strictly positive, strictly negative, or strictly not equals. Here, different versions of equality is what we would put down for the null. So that gets us started thinking about all this stuff. The other things we want to talk about right away is, notice it says parameter everywhere in the alternative hypothesis. It says it again in the null hypothesis. And then on the right, we have so-called hypothesized values. The hypothesized values comes from the context. So something in the wording of the problem is going to indicate what should go on the right side here. And whatever it is, it's maintained in the null hypothesis as well. Other thing that's tricky again is, because it says population parameter, you have to be really careful. There's loads of parameters we could be discussing. The parameters we'll be dealing with can be thought of as a two-way table like this. Here's the parameter. And here is the variable. So if your variable is quantitative, then our parameter that we're going to be testing hypotheses on is going to be just mu, the population mean. So that would go into all of these positions here. If we had quantitative data, think, for example, the last problem right over here. This was quantitative data that we were taking a look into, and the parameter mu that we discussed could have been placed into the alternative and null hypothesis if we did this as a hypothesis testing type of problem. So that's one parameter that can go there, but that's not the only parameter we've seen. We've seen also sigma, but we're not doing hypothesis tests on sigma on this course. We will do hypothesis tests on a parameter p. We introduced this one in chapter 13 on an example. This will be for when the data is categorical. And by categorical, we mean specific kind of categorical data, two outcomes, or two categories, which we'll call either a success or a failure if we have a categorical variable with just the two categories. P would be the population proportion of successes. And we'll be getting really into the statistic once we're into chapter 19, all about categorical data. That's pretty restrictive, just two categories. We'll look into chi-squared methods where there can be any number of categories larger than two, finitely many categories, and even more chi-squared procedures when there's two-way tables and so on. But for the moment, these are the two parameters that we were thinking about the most. They'll go into these positions here. We just have to find our hypothesized value, and then we're all set with the hypothesis testing. Well, any questions so far, folks, looking at this formation for the hypotheses? Okay, one last parting thought when we were looking at all these. Turns out these three alternative hypotheses all have a name now. They're all a flavor of doing a type of hypothesis test. For this one, the greater than sign, we would say that this is a right-tailed test. We call it right-tailed because we're going to be using probabilities. The probability is going to be on the right tail of the normal distribution. We'll call those probabilities p-values. and they'll inform us whether we're going to reject the null hypothesis or fail to do so. This one, it's got to be called a left tail test. And this one, with the not equals in the middle, this one's actually pretty special. This one is the so-called two-tailed test. And what's special about this one is, there's lots of options here. We have to select the right option in every new context. But this one is the default in every kind of situation. We need to have very specific reasons to do a left tail test. Something in the context has to tell us. That's what the researchers wanted to determine, or something has to direct us to a right tail test. Lacking any of that information, we always default to the two tail test. So let's say here, this is the default test. And another nice thing about this two-tailed test right here is if we do a confidence interval at a specific level of confidence, then the two-tailed test analysis would give you the same kind of conclusion. So that's helpful in a way. But one thing is missing with the hypothesis test. You either reject the null hypothesis or you fail to do so. If you reject the null hypothesis, essentially all you're saying is the parameter mu, the population mean, is not equal to some hypothesized value. Then the procedure is just over. And that's kind of weird because there's no estimate there. In that sort of sense, if you do a hypothesis test, that's only really one stage of the analysis. There should be a follow-up analysis where we also give an estimate of the parameter all at the same time. And this is the only hypothesis test that matches up with a confidence interval analysis, at least the confidence intervals that we described. You do a right tail hypothesis test and you want to do a confidence interval right after, our confidence interval, being two-sided, can give a conclusion that's contradictory to a right tail test or left tail test. That's kind of frustrating in a way. There's a resolution to it. You can actually make a confidence interval that goes from an A value off to positive infinity. But our author doesn't go quite to those kind of weird intervals. We just had an interval that has finite values on both sides, only matching up with this test here. So lots to consider and talk about. After considering all these, example 5 is just all about writing down some really fast and simple hypotheses. Before we go and describe how to get the p-value, what this is describing from the right tail, left tail, or both tails from the normal distribution. Well, before we go take a look at example 5, any questions for what we said up here, folks? Okay, well, let's take a look at this problem then. It says in example 5, for each of the following situations, define the unknown parameter using the context and write the null alternative hypothesis. So our first step on this one is just to say what the unknown parameter is. But we've got options. We need to know, are we talking about mu or are we talking about p? Anyone see which would be the right parameter in this problem? Sorry, go ahead. Yeah.
Would be P because it appears that the mean is given as 60, as it states, 65% of the population is in seatbelt compliance.
Yeah, that right there is pretty much the giveaway. When they gave a value like that describing the population, 65% means 65% of the population is classified as a success. The remaining 35% of the population classified as a failure. That means we're looking at categorical data, exactly two outcomes, and we can talk about P, the population proportion of successes in this situation. So good call. That percentage alone is kind of a dead giveaway. We're dealing with categorical data. Also, you can think in terms of elimination as well. If it was mu, there has to be a unit there. Maybe we're talking about time, so something in hours, maybe distances, so something in miles. But there's no indication of a unit, no indication of quantitative data whatsoever. So we're dealing with that parameter P this time. We can start by saying P equals the population proportion of what goes to the right here is the success in the problem. The success is what the problem seems to be mostly interested in. We have seatbelt compliance. So there's seatbelt compliance and seatbelt non-compliance. But if we said 65% of those drivers were compliant with seatbelts in 2008, seems like this is what the success is all about, being seatbelt compliant. So P is a population proportion of seat belt compliant drivers in Massachusetts and just to be specific, we're talking about a parameter. Let me insert here all drivers, not required emphasis, but it's good to think about all being there to remind us that's why it's a parameter. It's discussing the population now. So proportion of seat compliance for all drivers in Massachusetts, not in 2008, that's a long time ago these days. Let's say in 2025, imagining that this problem is being redone in the current year, for example. So it says here, the state wants to know if it has changed. But you know what that implies right away is this was their best guess for the parameter back in 2008 for Massachusetts. That's a hypothesized value now. We're wondering if it has changed in the current year, 2025. And so we're making a comparison from a population as it was in 2008 to the population as it is now in the present. Much like that Fukushima meltdown problem, the population of fish changed in a big way after the meltdown. And so our population proportion P here is not the 65%. That's just the hypothesized value. So we can say down here, P naught equals 0.65. Putting the little zero there for P naught is a way to indicate we're dealing with the hypothesized value. We're not dealing with the actual unknown parameter, population proportion P, that we want to discuss. But this gets us started. We have a hypothesized value, we have a parameter. So now we can write down a null hypothesis versus an alternative hypothesis, HA. This is not the complete hypothesis test. What we also have to attach here is the significance level for the test. But we're working our way towards the full procedure bit by bit. This is the rough patch, just setting up the hypotheses. Now that the parameter P is defined, we can just throw it here and here. And if we do reject the null hypothesis, we just read out what the statement says using our guide for how we defined P in the first place as our overall conclusion. Now, next thing we want to do is decide what goes on the right-hand side. It's a hypothesized value, so we put in 0.65 here, 0.65 here, and this is the question that they want to address. The state wants to know if it has changed. I guess that's not exactly a question, but it implies a question. If they want to know that it has changed, well, what does that feel like? A right tail test, a left tail test, or a two tail test? Something in there. Yeah, go ahead.
Would it be a two-tailed test because you want to know the before and after?
Absolutely, good call. When it says we want to know if it has changed, that's absolutely the two-tail test right here. So we'll go not equals. And you know what? If we weren't sure, just go the two-tail test as the default test. That's always probably the better strategy. What makes that a pretty good strategy too is some people in statistics have really rather strong opinions. Our author has pretty strong opinions on some of the things he writes. And one big, strong opinion in statistics is that there is a huge cadre of statisticians that say this should be the only test you ever use. I think that's too strong of a real opinion to apply in practice, but there are people out there that strongly believe you should only give the two-tailed test. So when we came down here on the problem and it didn't say the state wants to know if it has increased, we should just definitely put the two-tailed test. There's no indication of a direction whatsoever. That means we're going for that analysis. They didn't say, for example, they want to know if it has decreased or increased. We're checking for both directions. Yeah, go ahead. It kind of depends on sample size because skew can be a really big problem. But the good news is, if we look at a really fast graphic, even with really, really skewed data, it can be overcome. You can use the fact that the central limit theorem causes this kind of convergence to the normal distribution, even at really large sample sizes. So in certain situations, even if we have skewed data, central limit theorem still works for us. We'll later be going on to a t-distribution, but the central limit theorem is part of what works under the hood for that distribution as well. So even for highly skewed data, we should be okay. But if the sample size is low and skewed, now we have some big problems. It could potentially inform a different direction here, depending on the skew, but more likely, we would divert to something called a non-parametric test that doesn't worry about the skew of the data. It would use the sample's median instead of the sample's mean. Redoing the analogy before where if our data is too skewed, we measure the center with the median as opposed to the sample mean X bar.
Yeah.
Absolutely, yeah. When these so-called parametric tests, because they depend on these parameters, fail, there's the non-parametric tests. Sad news about those is that chapter 15, we're going to discuss the power of these hypothesis tests. It's going to be the power of correctly rejecting the null hypothesis when the alternative is true. The power of a parametric test is a lot higher than the power of a non-parametric test. So if we're forced into one of those, our conclusions are potentially quite a bit weakened unless there's a very strong and noticeable effect that could be detected in the population. But there's always good things to do, even when the data starts to get ugly and nasty. Other questions at the moment? Okay, well, this was setting up hypotheses for categorical data. And this one is setting up hypotheses for now quantitative data. We looked into this problem before, but now we're looking at it in full. This is really the first steps we would take if we're going to do a complete analysis on these data that we see right here. So just a reminder of the problem, we're talking about the ankle brachial index. It's a comparison of blood pressure in your arm to the blood pressure in your leg. And the comparison there is healthy at 0.9 or higher. And if it's below, it could be an indication of different diseases, arterial disease being something that I'm sure is very, very devastating. So really serious data. And it looks like this first paragraph is just context, but actually there's something really important here. That 0.9 value, that's the cutoff for when we go from being healthy to unhealthy. So let's pay really close attention to that, because they wouldn't have given us that information unless it was really useful. Well, sometimes statistical problems give us a lot of fluff that we have to cut through, but that looks like it's directly important. 0.9 or greater, let's capture that as well. So next, in a study by these folks, it said the researchers obtained the ABI of 187 women with peripheral arterial disease. The results were an mean ABI of 0.64, standard deviation at 0.15. And we want to know, at the 1% significance level, do we have significant statistical evidence to conclude that, on the average, women with peripheral arterial disease have an unhealthy ABI? So that's the research question they want to address. We know a healthy ABI is 0.90 or greater, so these two comments link up with each other. And we have something interesting that's new here as well. It says at the 1% significance level. This is another part of the hypothesis test, and it's analogous to, say, the confidence level for a confidence interval. Sometimes the problem will tell you, do it at a certain level of confidence or a certain level of significance for a hypothesis test. Other times, we have to decide for ourselves what's appropriate. But our data is quantitative, so we'll start off with mu. We can say mu is equal to the population mean we have to say the mean of what quantity specifically, what gave us a quantitative variable, in other words. That would just be the Inkel-Brackell index. I'll just call it ABI. So the population mean ABI. So this is the variable that we're dealing with. And next we have to mention the population in question. They sampled 187 women with peripheral arterial disease. So sample always comes from the population. This implies the population would be then all women with that particular disease. So our parameter is the mean population mean ABI for all women with peripheral arterial disease. So now we've got our parameter down, we can set up two hypotheses. Let's say it this way: test H naught. Notice we don't put equals, we just put a colon. It's just going to be a statement that we write in against HA, the alternative hypothesis. We'll write here P equals. Once I get the eraser going, let me try again. P equals. Here we have to decide on the test, so we don't want to fill in a symbol just yet. And now we need the hypothesized value that's going to go here and here. Anyone spot what it ought to be? Absolutely. This right here is implying the hypothesized value used in both hypotheses. And the way to kind of connect the dots is, with this research question right here, they are asking, did the data provide significant evidence that conclude that, on average, women with peripheral arterial disease, sorry, that's going to be a mu, not a p, let me fix that right away. That should be a mu. That should have been my guide, but I'm not too sure why p snuck in there. It's asking if we have evidence to conclude on average, this group of people have an unhealthy ABI. So that tells us we're talking about this measurement right here. This is the cutoff for when we go from healthy to unhealthy. So that is our mu naught. So 0.9 is going to go here. We'll go here. And now last remaining thing we have to do is decide which test should this be. We're not sure. The two-tailed test is the most safe one to go with, but this one is not a two-tailed test. Anyone see which one it should be, left-tailed or right-tailed? Let me see here. If we go right-tailed, that would be a greater than in this direction, and that would be at the healthy level, being 0.9 or greater. Kind of a tricky the way they stated this. It's almost offensive, right? The best way to write this problem is to say an unhealthy ABI is 0.9 or lower. But this problem is written down in kind of an honest way. When people give you information because they want help with statistics, they're going to give you a bunch of stuff that doesn't fit perfectly, and we have to contort into the right directions. So this was really left-tail test because we're testing for an unhealthy ABI, switching around the direction of this data here. It's not a great exam problem, but it's a pretty honest homework kind of question right here when we have to do that kind of contortions. So we're going to test this mean at equals 0.9 against the mean is actually less than 0.9 at a 1% significance level. This part will just be paraphrased by saying at alpha, that's our shorthand for the significance level, equals 0.01. So we've mostly did this whole hypothesis test. This would be a good stopping point, but I'm pretty sure some people have some interesting things to say about this. This is the discussion we were mentioning earlier. In our textbook, our author will only put equality right there. To some people, that might feel pretty uncomfortable depending on how you learn statistics. So there's another version if you didn't want equality. You could go like this. If this is a less than, these hypotheses are supposed to be completely diametrically opposed in the sense that whatever is here, you need to take the negation of it and drop in a statement here. So if it's a less than, you can go greater than or equals over here. And that's another valid way to state the null hypothesis. So for a lot of folks, especially if you're taking the biometry lab, I believe this is how your null hypothesis would have been set. But just to reiterate that there are options here, let's leave it this way on this one, but say for H naught, mu equals 0.9 is acceptable. Our author, again, has really good reasons for equality here. We'll discuss some of them in chapter 15. One of the reasons is there's infinitely many different values here. There's the 0.9, that's right at the cutoff. There's the 1.3, maybe 7.8. That's a huge ABI. Don't know if it's reasonable or not. But any value greater than 0.9 would be reasonable for what you could be. And now that tells us there's really infinitely different p-values we could get, all based off different values put in here. But we want the largest p-value possible so that we don't make a mistake by just rejecting things incorrectly. And the largest p-value possible is at direct equality. That's a major reason some authors are included, only put equality on the null hypothesis. It's the actual value you're using, 0.9, on every hypothesis test, whether or not you put equality or greater than or equals. That's the next portion that goes into the formulas. But aside from that, next thing we need to describe is what are the p-values and how the formulas go. Any questions at all when getting these hypotheses set up first? Okay, so going down to the next portion, here's how we're going to conduct the hypothesis test, get a p-value out, and make a conclusion. So this is where it's really starting in earnest. It says, gather a simple random sample of size n. We expect that we want a random sample. We're going to say the population is normally distributed, but we'll weaken that assumption in chapter 17. It has to have an unknown mean mu. In just this chapter, we'll essentially pretend we know what sigma is, just to describe how the methods go. And we have to also state a significance level alpha. This is going to be a cutoff value that tells us whether we reject the null hypothesis or fail to do so. And when you're designing a study like this has to be put down in stone, and it can never be changed once it's set. Neither can your hypotheses. So no matter what the data looks like, if that value is ever changed, it's considered to be massively unethical. In fact, if you get government funding, there's a good chance the government is watching the progress of your study. You're submitting proposals. You're saying what alpha will be. And if you give a conclusion where anything changes, you might be in the hook for refunding some of that money. You can't make these big unethical changes in the middle of a study. So once we determine what that level alpha is, we compute the test statistic z. For people who have taken statistics before, you might recognize that to be just an ordinary z-score. We measure the distance between x bar and mu naught, the hypothesized mean. And we measure that in terms of the standard deviation right here, coming from the central limit theorem, where x bar is distributed normally. With the true mean mu, it's unknown, but there is a real mean right there, and standard deviation sigma over the root of n. So notice it's mu naught here, not mu. We don't even know what that value is. But the very first step in hypothesis testing is you assume that is true. Let's say that right here. In hypothesis testing, we assume H naught is true. Assuming this is now the truth of the population, this mu is now mu naught under that assumption, which may or may not be correct. But when you make that assumption, back to the test statistic, it's going to measure the number of standard deviations away from your actual data, its sample mean, the mean you hypothesized in terms of standard deviations. If this is a lot of standard deviations, anything beyond 3 is a lot, that tells us we have significant evidence against the null hypothesis. But we need to translate that into a probability to check against alpha. So that's so far the logic of a hypothesis testing. This is just measuring the distance of your data and the claim you've made about the population in terms of number of standard deviations. And then down over here, we'll calculate the p-value based off of the test statistic z. Well, any questions, folks, so far, before we go and just describe our p-values next? Okay, these are pretty short descriptions. If we have a right tail test, the situation would look about like this. This is the curve N01, the standard normal distribution, centered at exactly 0, and it should be, because this is a distribution that we're using for our test statistic z. If we subtract off the hypothesized mean, the new mean for this variable z is 0, right at 0. And if we divide by the standard deviation, we've also standardized to a standard deviation of exactly 1. So just like with confidence intervals, we always work on N01 either to get the critical number z star or to get the p-values that we're about to describe. So we're centered here at 0. Let me give a special color to this. It's kind of the superstar here. In a right-tailed test, our hope is that z is clear out here, but it can be anywhere. Exactly 0 potentially, way over here on the left. But if it's over here, this has a chance of being significant. We might reject the null hypothesis. And that's your p-value right there, that area. It makes sense, it's the right-tailed test. So we get the area in the right tail. So that's your p-value. In our syntax in this class, it'll be p norm z lower dot tail set false. So that does it. Notice I didn't have to say what the mean is or the standard deviation is, because we're using the standard model. The p-norm function is going to assume that if I don't say anything beyond z. So that's where we get our p-value there. Again, we hope our p-value is small because it's going to be the probability of getting as data as extreme as we have under the assumption the null hypothesis is true. If that probability is small, we're saying this is an unreasonable assumption to make in the first place, now supporting one of these alternative hypotheses below. But the next picture could look like this if it's a left tail test. Here's the normal distribution again. The test statistic z, we hope is clear out here to make it significant. But if it's out here, your p-value is huge. We're probably going to fail to reject the null hypothesis. This is what your p-value would look like this time. A really large area, it seems like it's about 40% or maybe 35% based on how it was plotted. And the p-value this time is going to be equal to p norm z. That's kind of nice syntax, right? That is all you have to say. Kind of convenient in a certain sense. That's because it's going to automatically generate the area to the left. It'll assume the value 0 for the mean, 1 for the standard deviation. So all you had to do is calculate your test statistic, plug it into a p-norm, and you're on your way for the left tail test. Sadly, for the two-tail test, this is the default test. It's also the more complicated one to describe. I typed this out verbatim based off what the author said. Twice the area under the curve to the right of the absolute value of z. You know, it could have been to the right or to the left. You have options to get the same symmetric area. But let's describe what it is. And then we'll be ready to describe how to make the decisions for the hypothesis test. So in a two-tail test, when you go to calculate your test statistic z, it can be either positive or negative. We don't know where it's going to be. I just have to drop something somewhere. Let's assume the absolute value of z is in this location. I put an absolute value because, again, if we don't know if it's positive or negative, we want to draw one diagram, I can force this positive by just throwing absolute value on it, and here's Z. That's just one of the two-tail tests. Remember, there are two on this one. So symmetrically, to the left of 0 is negative absolute value Z, forcing that test statistic to be negative now. We get this area. And if we follow our author's advice verbatim, this is what the syntax would look like. It looks like it's two probability computations, but the area on the left is exactly the area on the right because this normal curve is perfectly symmetric. So you could just take this, go p-value equals 2 times p-norm, and annoyingly, you need to know what the sign of Z is to get this just right. Unless you hit it with the absolute value, now you force the sign. So you can go ABS for absolute value of Z. Then, because our author specified this to be the right, if we decide to follow this verbatim, we would have to go lower dot tail equals false. And that syntax would do the job for us. Honestly, not my favorite way to do it, so we'll describe another one next. But does that make sense to folks on what this is saying? Okay, so for the second version, you could also say, or p-value equals, I want to double that area. It turns out that's a little bit more convenient just for our syntax. P-value will be 2 times p-norm. But if I want to double the area of this tail, you have to know the sign of Z, or just take the absolute value of it, negate the absolute value so you forced it in the left tail. We need negative ABS-Z for absolute value Z. Then that's all you would have to say, because we're automatically generating the area to the left. We're doubling it at the same time, and so now we have the area in both tails if we go that route. For me, I kind of like going this way, but for the sake of making the book more readable, this would be the more natural way as well. Well, any questions, folks, on getting the p-values? Okay, there's lots to describe to this kind of stuff, but the good thing is, once you do this once, and then we're in chapter 17, we're going to redo this all over again with the t-distribution. It's the same stuff. Even when we're in chapter 18, we're handling 2 different means simultaneously, same stuff. So if you can specify this once, you've got a way to calculate the p-value in just about any situation. So now, once you get your p-value, it's just a probability from the normal distribution. Here's how we make a decision on whether we reject the null hypothesis or fail to reject it. The trouble here is there are only ever 2 conclusions you could ever make. Let's say this loudly right here just as a big reminder. Oh, I guess we already said it down here. One conclusion we can never make is that we accept the null hypothesis is true. Think again in the logic with the court of law. Suppose your defense attorney is really good and we could never establish that you're guilty. That court of law didn't establish you're innocent either. It just failed to show that you were guilty. No one's declared innocent in a court of law. That's really weird, except for at the beginning. Let me say this in a better way. You're declared innocent at the beginning of a court of law. Once everything is concluded, you're never declared innocent. You're either found guilty or there was a lack of evidence to find you guilty. Kind of weird in a certain sense. Hypothesis testing matches that logic exactly. So these are the only conclusions we can make when we go to write out a conclusion to a hypothesis test. Recall what alpha is. It's the significance level stated in the problem. And typical values we saw at 0.1 are these. Alpha could be equal to, say, 0.10, or alpha might be set to 0.05. There's nothing specifically important about these cutoffs. If you set one to 0.09 or 0.04, people might think you're weird, but there's nothing wrong with it legitimately. People just seem to land on these round numbers for some reason. Another one that we just saw is alpha equals 0.01. So if we go to calculate a p-value and we find our p-value is below the significance level alpha, this is the good outcome. We reject the null hypothesis, and our conclusion is essentially going to be saying this. We have found this is significant statistical evidence that our alternative hypothesis is true. So we like that outcome. But if the p-value equals alpha, that'd be really weird, but if that ever happened, or if it's greater than alpha, more likely, we have failed to reject the null hypothesis, did not mean we found it to be true. We failed to find any evidence against it. An absence of evidence is not evidence the null is true whatsoever. We say in this conclusion, the study failed to find significant statistical evidence that whatever that claim was is true. Doesn't seem like a very satisfying conclusion, but that's important. In the sciences, we need to publish when we fail to find that evidence as well. If you gather a bunch of studies where this has actually failed, a meta-analysis can be performed. And there could be significance, even if we look into papers where a bunch of things got rejected on the same problem. So these are important to be published even when this happens. It's just probably no one's celebrating this time. And with all that said, we're just about ready to go through a full problem down below. But any questions at the moment, folks, with what we've discussed so far? Okay, final parting thoughts are, we made one statement, that the two-tailed test will give the analogous conclusion as a confidence interval if you tune it just right. And what we mean by that is there's corresponding values for confidence levels as well. If you're doing a confidence interval analysis, maybe you did a hypothesis test, you found that the alternative is significant, we found evidence it's true, people are going to want to know the estimate of the parameter anyways. So if that's the case, we would give a confidence interval analysis, and the corresponding confidence level would be C equals 0.90. If your test is at alpha, significance level alpha 0.10, a follow-up analysis has to be a 90% confidence interval. Likewise, here it'd be at 0.95, here it would be 0.99, and the larger comment is that alpha plus C has to be exactly 1 if we're trying to give an equivalent follow-up analysis to our two-tailed test. So that's the full write-up of what a hypothesis test is. It takes a lot of oxygen to say all this stuff. This is a good conclusion to, or statement to always come back to. And example 6, we're going to put all this into practice and see if we can provide a complete analysis to these data. Well, any questions or comments first, folks, before we launch into all this stuff here? Okay, let's take a look at what we're getting into. It starts off by saying the Board of Health of a particular state, let's say Idaho, makes it feel more immediate, was called to investigate claims that raw pollutants were being released into a river flowing past a small residential community, say Idaho Falls, something like that. By applying financial pressure, the state was able to get the violating company to make major concessions towards the installation of a new water purification system. So we know how that goes, though. If they really installed this water purification system, we also have to double check, is it working as intended? The company itself could be doing everything right, but maybe this new purification system was just not engineered correctly to no fault of their own. There's a problem here. But it goes on to say, before that new water purification system, which is probably costly, heavy, hard to engineer, in the interim, in the meanwhile, different production systems were to be initiated to help reduce the pollution level of water entering the river. So, to moderate the effect of the interim system, this is what we're really doing the statistical problem. The company has promised to reduce their pollution level, and we have to check that as well. So we're monitoring the effect of the interim system. In that monitoring, a random sample of 50 water specimens has been selected. So we've had a sample size, N is 50. They did say it was a random sample, so that's encouraging, but we don't know what random sampling design was used. It's measuring the dissolved oxygen count of water in parts per million, taken throughout the month at a location downstream from the plant. And this is a pretty good indication of pollutants being in the system. If something nasty is going into the water, it can potentially kill some of the local flora, fauna, algae, that kind of stuff. And this might be where you start to see an effect, the dissolved oxygen in parts per million. At least that's what I think is going on. That's why we're interested in that figure there. Then it goes on to say, we have a sample mean of 5 parts per million obtained. Dissolved oxygen content is what they're referring to. So sample mean is at 5.0 parts per million. And it says next, assume that the population standard deviation of dissolved oxygen count in the water at this location is 0.07 parts per million, or rather 0.70. They said population standard deviation. So because of this word right here, it gave us a sigma value. This is where the problem starts to become a little bit uncomfortable. But if this figure is real and accurate, and if we think it wouldn't change depending on what's happening with the internal system, reducing the pollution level, it might be a reasonable assumption. But when we go to give a conclusion here, this could be a part where everything could be challenged. The company itself could say, your statistical method relied on assumption of a parameter. They could challenge our whole study just based off that right there. So that's one reason we need a better method. But we're getting to chapter 17 slowly. Here's the next part of the problem. This is a question being asked, so it's basically the alternative hypothesis right at this statement. Is there evidence that the mean dissolved oxygen content of the water is less than 5.2, the mean reading of this location over the previous year? So for the prior year, dissolved oxygen content was 5.2. Sample mean is at 5.0 in the present. It looks like the internal system reducing the pollution might be really working. Well, that's what the company would say. We know with statistics, the sample mean being slightly below historical value 5.2 is not good enough because there's variability in statistics. Standard deviation is part of the story here. That might not be significantly lower than 5.2. So we're going to find out by performing a complete analysis if do we have evidence that the true mean, we're talking about the unknown parameter now, is truly less than 5.2. There's a stated level of significance here at 0.05. So when you read this out, think alpha is 0.05. And that ties into this table right over here. Once we compute the p-value, we'll check it against alpha, and if it's less than it, we will have significant statistical evidence for our alternative hypothesis, whatever it might be. So that's the work of this so far. Now we'll run through the complete analysis, doing all these 4 parts below. We want a practical question that requires statistical inference to be stated first. Let's write out something kind of generic. We might say, do we have evidence that the dissolved oxygen count, let me try to spell that better, is below 5.2. I didn't say out all the context here, but there's something big missing in this question or this statement right here, the practical question. And let's see what's missing altogether inside this. It's really kind of small. Not necessarily. Here we're really just trying to indicate what the practical question is going to be without using too many symbols. Potentially, yeah. That would be adding a little bit more context to what we're saying right here. But even if we said there's dissolved oxygen count in the water is below 5.2, the thing that is kind of missing here is, seems like we're talking about one measurement. That's not what we're doing at all here. We're not talking about getting one measurement of the water downstream and checking that measurement. We're talking about, on average, all of the measurements, if we were to take them, is it going to be on average below 5.2? So we're talking about means and parameters, not single observations whatsoever. So we can say here, on average, just as a catch-all. So this is a way to kind of indicate the actual hypothesis test is relative to the population mean, which is the population's average. So this is the real question we're trying to answer. It's not about one measurement. One measurement might read high, but we want to know the measure of the average of all measurements, talking about the parameter. Is that below 5.2? If it is, we'll say the internal systems are working. If it isn't, well, we will not be able to accept the null hypothesis, so we have to bake that into our conclusion as well. Keep in mind, these are the only kind of conclusions we can give, so we'll cite this chart as we go to give them. Well, that's how I'd probably write out the practical question on this. There's a lot of things you could say here that would be equivalent. Yeah, go ahead.
Because we're comparing the sampling to the population.
Exactly, yeah. This one is estimating the unknown population mean already, absolutely. So all of our conclusions, all of our testing, and the confidence intervals themselves, always about averages, never about the single individual. Other questions so far? Okay, well, the planning phase for this goes a lot different than with confidence intervals, but it starts off the same. We start by indicating what the parameter is, and that makes sense, right? Because if we're going to state the null and alternative hypothesis, it's always stated in terms of that unknown parameter. So we need to say what it is right away. It's not that 5.2. This was the value for the reading over the previous year for that stream downstream of the plant. So this value 5.2 is the hypothesized value. We're checking against historical data now. So we have hypothesized value, because we're dealing with quantitative data, X bars and mu's. We'll call this one mu naught equals 5.2 parts per million. So that's going to be rolled into our hypothesis as well. So mu is not that historical figure. It's the dissolved oxygen count parts per million as it is currently, with the interim system in place and the company supposedly reducing the pollution level. Simple means seems to support it, but we still need to say mu is going to be equal to the population mean dissolved oxygen count in parts per million downstream of the, got how they indicated this, downstream from the plant is what they called. So that's the thing that we're going to test in hypotheses. Now we can write out a null. We'll test H naught, that mu is equal to whatever the hypothesized value was that we stated. We stated it's 5.2 parts per million, so it gets just dropped right into this location. So here it is. Units aren't necessary, but sometimes it's a good call to throw it in unit anyways, because it'll help us when we go to make an interpretation or a conclusion at the end. So we're going to test that against or versus an alternative hypothesis that mu compared against 5.2, oh, that was supposed to be a highlighter. So this is what it stands so far. Something in the practical question over here, indicated this way, indicates a direction for this problem. But if we never saw it, again, a not equals here is the best call to make. If you put a not equals, but it was meant to be a right tail test or a left tail test, you might lose a single point. It won't be a major concern. I would still think it's a good call to put in the two tails at default. until you personally had strong enough reasons to change it. But they did ask here, right where the question came up, if there's evidence that the dissolved mean oxygen content of the water is less than 5.2. Only because of the less than right here, a direction really is being asked in this hypothesis test. So we have to go a less than right there as well to match it up. So this part right here is only because of the less than stated right there. Next thing we should say, we're testing these hypotheses at the significance level of 0.05. We usually just paraphrase that by rewriting the symbol. Alpha equals 0.05. Once we compute to get our p-value out, we're looking right there to determine what is the conclusion of our hypothesis test. So we're running through it. Next thing we have to do is check conditions. But one thing I should mention is you might have noticed this problem is a lot different than when we check conditions for the confidence interval. The data is somewhere, but I don't know what the raw data even is. All we know is the summary value, the sample mean. They didn't even give us the sample standard deviation. We just know it's based off 50 observations. So in the LAC, let's say it better this way. When we lack raw data, well, that means we can't produce a histogram to do condition checking to determine if it's reasonable. Our sample data came from a normal population. So we have to be a little bit more clever and now judge by the sample size. So we'll say here, when we lack raw data, we use the sample size to help with condition checking. And here's how it helps. The sample size is pretty big in a certain sense. We have a sample size at 50. Now, the big machinery that works, whether it's a confidence interval or a hypothesis test, the big machinery that's helping us with all statistical inferences is essential limit theorem itself. We can return to this rule of thumb that says, for most populations at sample size larger than 30, the essential limit theorem is highly effective. Your underlying population has to be tremendously skewed, something pretty nasty, for this to be a rule of thumb that gets violated. But our author does admit these do happen, even though if they're rarely encountered in practice, they're things we should be aware of can occur. So we're feeling pretty happy with the sample size of 50. Here's a bigly right skewed population, right around sample size 50. Even that one gets corrected. Essential limit theorem shows we're approaching an actual normal distribution. So back here, sample size of 50 is hopeful for us. We can say for condition 1, since n equals 50, the central limit theorem can, let's say it this way, is likely to be effective even if that underlying population, I'll just say the underlying population is skewed. And I'm kind of realizing I did this one slightly out of order. Sorry for the distraction on this one. I believe this was condition 3 that we checked with the confidence interval. Condition 2 was we needed a value of sigma. And condition 1 was if we had random data. You don't have to state them in a specific order, but the notes are hard to read without that parallelism. Sorry for forgetting about that. The problem did say we have random data, but we have a random sample. So we have a random sample. And lastly, we're also provided a value of sigma. I think it's, the 0.70. Sigma equals 0.70 parts per million is given. So overall, it looks like we're not in a bad place with this kind of data. But this isn't perfect. We don't know the sampling design. That's one issue. We don't know how reliable this is because they changed their production systems, reducing the pollution. Mu changed. Why can't sigma change is a big question, and it's an honest question. Result deserves resolution there. And sure, rule of thumb says sample size bigger than 30 is effective, but unless we actually see the sample data, how bad it could be skewed, we don't necessarily know if this is a met assumption as well. So sample size 50 might not be enough if the data is skewed enough that we are actually looking at. So we can say, overall, the conditions appear to be met. But when we give an overall conclusion at the very bottom, we have plenty of things to complain about. So we'll mention some of these shortcomings. We'll say our study can be challenged on this basis, and so on, just to give a very honest conclusion. As long as everything goes right, we might have a nice statement to make there. But that's the tough part about setting up a confidence interval or a hypothesis test. The planning phase is involved because we're doing multiple things: the parameter, the null, the alternative, and the significance level. For condition checking, if we have raw data, we'll produce a histogram. Without it, we'll argue in this kind of way. But for now, for the necessary computations, this is the fun part. We need a test statistic, then we get a p-value. Any questions first, folks, before we go for those last portions? Okay, let's write out formula for the test statistic z. Z is going to be equal to our value x bar. We measure a distance from x bar to a hypothesized mean, mu naught, and that distance is in terms of standard deviations. So sigma divided by square root of the sample size. So it's a good call just to write in that formula. It makes us more comfortable with using it. Then come back up here, and I think we can get most of our information from that screenshot. Just plug them in as we see them. So x bar is 5, I'll drop units at this stage, minus mu naught, I didn't quite grab that one. I believe that was 5.2. That would be in our null and our alternative hypothesis. Sigma, stated in the problem, is 0.7. And we're dividing that by square root 50. So there it is, folks, all the data from above in the problem. We haven't used RStudio all day today, and we're almost about 9 minutes left in class. That's kind of impressive. But here's one way that you can run all of this kind of syntax. Go z gets 5 minus 5.2. We want parentheses for the numerator and for the denominator. 0.7 divide by square root 50. So let's run that. I'll hit Z again just to output it. And we have that our sample data was actually quite far away from 5.2. It's over 2 standard deviations. So good value to round to here, I'd say would be 4 decimal places. But really, I'm going to keep the full precision and just add a new statement here on the script portion. But so far, it's negative 2.0203. Standard deviations, you don't have to mention that, but that is the true unit of the z-score. We're quite a few standard deviations away from the hypothesized mean. Next thing we need to do is decide, well, what test was this? Let's scroll up. It's a left tail test, just by that less than direction right there. And in the left tail test, this is all we have to do. P norm z does the whole job for us. It's kind of nice in a way. So let's run that next line. Our p-value is at 0.0217. So that's the p-value getting computed. Any questions, folks, on getting that next value down? Okay, once we have the p-value, we're still not done with this step right here. We need to go back up to the top, grab all of this right here, Let's just drop it down so we can refer back to it. And when we make a decision on hypothesis testing, we compare the p-value against the significance level alpha. So here it is at 0.05. Our p-value is less than that figure. We want small p-values. Small p-values say that this was really far away, that our null hypothesis assumption that mu naught is 5.2 is unreasonable, because the chance of that happening is so low, below the level of significance, we get to say here, we will reject H naught. And see the table above, it's easy to kind of forget these directions, but small leads to a rejection of H naught. So now that means we're nearly there. H naught is rejected. We found significant evidence that the alternative is true, and all we have to now do is just simply say that. Well, any questions at the moment, folks, before we go to put down our conclusion? Okay, this one was kind of an easier hypothesis test in the sense that when you fail to reject the null hypothesis, you have to be very touchy with how you write your conclusion, because no language could ever be written in that interprets it as you've accepted the null as true. It has to be very well avoided. But here, if you accept the alternative hypothesis, we just read out that statement as we see it. We'll say, we have significant statistical evidence that mu less than 5.2. We can't say that. We have to write out the whole conclusion. It's okay to paraphrase this a little bit if you've written it down once. I think it's a reasonable thing to do. That makes it feel like less of a chore writing it down mu twice. It does feel like it's redundant when you write it once in planning phase, again in the conclusion phase. The only reason I ask for it is I have found after teaching this class over 10 years, if you say it once, you have a better chance of saying it correctly here. Whereas if you've never said it in the planning phase, it's hard to say what the parameter is all of a sudden down here. So it's kind of a busy work part of the problem. Feel free to paraphrase it a little bit, no harm done. We'll say we have significant statistical evidence that the mean, I dropped population there, dissolved oxygen count in parts per million. I'm going to skip the part where it says downstream of the plant. It's in context now that we've written it once. Is, now we can say less than 5.2 parts per million. This would make a lot of people happy making this conclusion, in particularly the company that runs this plant. We found evidence that in the interim, when they reduced their pollution levels, they really did that based off our statistical test. Again, we can make a lot of statements about what all went wrong right here. And I think the bigger thing was we couldn't verify directly how well the central limit theorem was looking by taking a look at the sample data. So I would say here, as just one extra addendum to this, these conclusions may be challenged if the sample data, I don't want to say if the sample data is skewed, because sample size 50 can overcome that. We want to say if the sample data is something strong, pathologically skewed, or maybe you might say violently skewed, anything along those lines that indicates an abnormally high amount of skew. That's a place where this would challenge all of these conclusions. But we did it, folks. This is running through a full hypothesis test. We're not completely done with this chapter. I did want to discuss some concept questions down below, so we'll have to return to those when we come back on the next class meeting. But now that we've done all this, keep in mind, whether it's a confidence interval or a hypothesis test, this isn't the end of this. We could have made a mistake. And if we don't analyze carefully what the kind of errors there are, there's a type 1 and type 2 error to avoid, we might not be too happy with how the significance level alpha was set or those kinds of things. So there's a lot of work to do in chapter 15 when we analyze how alpha 0.05 was selected in the very first place. But I think this is a good point for us to stop. I can't go too much further in one single minute. Any last questions, folks, before we call it a night officially? Okay, well, have a great day, folks. The chapter 14 due date will be pushed back a little bit so that we have the 1 week turnaround. So the only chapter that's due at the moment is the assignment number 4 relative to chapter 13. Well, have a great night, folks. If any questions come up, don't hesitate to reach out. I'll be happy to help.
Thank you.
Yep, take care. Thanks, you as well. Awesome, thank you.
Careful.
I will. Yeah, I have the same issue with my home stapler as well. Yeah,
Excellent weekend.
thanks, you too.